morning everyone. Welcome to Microwave Engineering video lecture series. In this video, we are going to discuss about what is directional coupler, what is the structure of directional coupler, the operating mechanism of directional coupler, its properties and applications of DC, and the derivation part of directional coupler that we are going to cover it in this today's video. So the main application of using directional coupler is to sample a small amount of microwave power. Directional couplers will be used for measurement purpose. That means if you want to measure a sample from a power flow in a measurement setup, then we can use this particular device called as directional coupler for understanding the power values. So using directional coupler, we can measure incident power, reflected power, voltage standing wave ratio, that is VSWR. That means by using this particular device, we can measure incident power, reflected power and VSWR. So this is also a 4-port waveguide junction consisting of primary waveguide and secondary waveguide. So we can see in this figure, this one is our primary waveguide and this one is our secondary waveguide. So we have total 4 ports, that is port number 1, port number 2, port number 3 and port number 4. So at port number 4, we have written as PI, that PI means input power. At port number 2, it is PR, that is received power. At port number 4, it is PF. PF means forward power. At port number 3, we have back power. That means basically this is our actual power flow. From this, we are taking a sample towards this, that is PF. And in this process, there is a possibility of reflected power towards this particular port. So directional coupler is a 4-port device. And if input is given to port 1, then power traveling portion from port 1 to port 2 is coupled to port 4 but not to port 3. Very important statement. That means let's assume, suppose we are giving input from port 1. Suppose if I am giving input at port 1, then the part of the power which is coming from port 1 will be coupled to port 4 along with the path towards port number 2, and there won't be any power at port number 3. Similarly, suppose if I am giving, let's assume, suppose if input port is port number 2, that means let's assume port number 2 is your input port. In that case, so our power will flow like this towards port 1, and this is our main power, and from that you are going to have a coupled power towards port 3, and there won't be any power at port number 4. So likewise, we can understand the operation of a directional coupler at each and every port. So we can understand this in detail. Suppose let's assume this is port 1, this is port 2, this is port 3 and this is port 4. Okay, this is our primary waveguide, this is our secondary waveguide. So in this particular figure, so we have seen that if input is given at port 1, it will be traveling towards port 2 and coupled to port number 4, and at port number 3 there won't be any output. So our figure will be like this. Power will flow like this and power will be coupled this, and there won't be any power. That is one possibility. That possibility is first case. Similarly, suppose I am drawing the same figure again. Port 1, port 2, port 3 and port 4. Okay. Suppose let's assume now we are giving input to second port. If we are giving input to second port, then the direction of power will be like this, and from this you are going to have a coupled power towards port number 3, and there won't be any power at port number 4. Similarly, the third possible case is, suppose we are drawing the same figure again, port number 1, 2, 3, 4. So in the first case we have given input at port number 1. In second case we have given input at port number 2. Now suppose let's assume give input at port number 3. Let's assume if we give input at port number 3, then our power will be flowing like this, and this power will be coupled to port number 2, and there won't be any output at port number 1. Okay, that is third possibility. And what is the last possibility? Last possibility is, this is our main waveguide, this is our secondary waveguide, this is our port number 1, this is our port number 2, this is our port number 3, this is our port number 4. Input at 1, that case we have discussed. Input given at port 2, that we have seen. Input given at port number 3, that also we have seen. Now if input is given at port 4, we will see what is going to happen. Suppose if you are giving input, then this power will be coupled to port 1, and there won't be any output at port number 2. So the main observation is, when we are giving input at port 1, we are not getting any output at port number 3. And suppose if we are giving input at port number 3, then we are not getting any output at port 1. Similarly, if you are giving input at port number 2, there is no output at port number 4. Similarly, if you are giving input at port 4, there is no output at port number 2. That means port 1 and 3 are isolated ports, and port 2 and 4 are isolated ports. So isolated ports we have discussed in case of magic T, in case of E plane, H plane, that we have discussed. So in case of directional coupler, we are going to have 1 and 3 and 2 and 4. So hence port number 1 and 3, port number 2 and 4 are named as isolated ports. This is the ideal case. So ideal case means we are claiming that there is no power coming from port number 3 here, port number 1 here, port number 4 here, and port number 2 here. This entire discussion is with respect to the ideal case. Okay. But in practical cases, we are going to have the backward power. So basically we have written input power as Pi, received power as PR, forward power as PF, backward power as P suffix B. Okay. So now we are going to understand what are the performance metrics of a directional coupler. So there are three main performance metrics of a directional coupler that we can remember with a shortcut name as CID. CID. C stands for coupling, I stands for isolation, D stands for directivity. Okay. So we are going to discuss what is coupling factor, what is isolation factor, what is a directivity factor, and also we are going to discuss what are the normal values of coupling factor, isolation factor, directivity factor, and what are the ideal values of coupling, isolation and directivity factors that we are going to discuss now. Okay, so the first thing is named as coupling factor. The symbol or letter used for representing this factor is capital C. Okay, so basically this is a ratio of input power to forward couple power, that is PF in decibels. So here we can understand this from this particular figure. So we are defining coupling factor C as ratio of input power. Input power is this one and forward power is at port number 4. This particular ratio, that is called couple, because if you are giving input power at port 1, obviously you are going to have a coupling power at port 4. That's why we are defining this C as 10 log base 10 Pi by Pf in decibels. That is called as coupling factor capital C. Next we are having directivity, that is D. It is defined as ratio of forward coupled power to backward power. So here ratio of forward power to backward power means at port number 4 we are having forward power, that is Pf. At port number 3 we are having back power, that is Pb. So if you are dealing with these parameter ratios, then that is called as directivity factor, that is D, capital D. That is capital D is equal to 10 log base 10 Pf by Pb. Pf is your coupling and Pb is your back power. Okay, that is in terms of dB. And the next one is isolation I. Isolation factor I, which is defined as ratio of input power to backward power. So that is, we are dealing with respect to these two. Input power to the back power PB, that is between port 1 and 3. So please remember, in the entire discussion, I am assuming that input is given at port number 1 and we are receiving output at port number 2 as received power and coupled power at port number 4 as Pf and back power at port number 3. So likewise, you can give input at any other ports like we have discussed here, and we can define the performance metrics accordingly. Okay, so here, so the typical values of a directional coupler, basically for the C is nothing but our coupling factor. The coupling factor will be 20 dB. The formula we are using is C is equal to 10 log base 10 Pi by Pf. So this is in terms of dB. So this is, the normal value is 20 dB. So if you put 20 here, we are going to have 20 by 10. So this is 10 to the power 2 we are going to have, that is Pi by Pf. Then we can write Pf is equal to Pi by 10 to the power 2 means 100. That is what we have written here. Pf is equal to Pi divided by 100. What does it mean? If the C value is equal to 20, C value 20 means coupling factor is equal to 20 dB. That means what? From the input power, 1/100th of the input power is only going to be there across Pf. That means 1/100th of this Pi will be there as Pf. That is the meaning of this Pf is equal to Pi by 100. Similarly, the ideal value of Pb is equal to 0, that we have seen. If Pb is equal to 0, if you put that Pb in the directivity formula, that is D is equal to 10 log base 10 Pf by Pb, what we are going to get? We are going to get D is equal to infinity. That means ideally Pb will be equal to 0 and as a result D will be equal to infinite. But in normal cases, D will be equal to 60 dB. So if you put 60 here, then this will be 10 to the power 6. That is 10 to the power 6. 10 to the power 6 on left hand side is equal to Pf by Pb, or we can write Pb is equal to Pf by 10 to the power 6. That is what we have shown here. That means Pb is very small quantity. compared to the PF. So what is PF here? PF is your coupling power and PB is your backward power. That means due to reflections, there is a possibility of getting backward power towards port number 3. So compared to the PF, the PB is very small. That is PF divided by 10 to the power 6. That means 1 by 10 to the power 6 of the power may come as a back power towards port number 3. That is the normal case for directivity. Similarly, the ideal value of PB is 0. If you put PB is equal to 0 in isolation formula, then we are going to have I is equal to infinite. That means the ideal values of directivity is infinite and the ideal value of isolation is infinite, and the normal value of C is equal to 20 dB, normal value of D is equal to 60 dB. Okay, so now we are going to understand what is the relationship between C, I and D. How to represent C in terms of D and I, or how to represent I in terms of C and D. That we are going to understand with the help of a relationship between CID. So for understanding this relationship, so we can take the formula for isolation as a reference. That is, the formula for isolation is I is equal to 10 log base 10 Pi by Pb. So if you take that as the reference formula, we can write this Pi by Pb as Pi by Pf into Pf by Pb. Pf cancel, you are going to get the same thing. So we can write I is equal to 10 log base 10 Pi by Pf into Pf by Pb. This Pi by Pf, that is basically we are having log A into B. Log A into B is nothing but log A plus log B. So we can write 10 log base 10 Pi by Pf plus 10 log base 10 Pf by Pb. So from our earlier definitions, 10 log base 10 Pi by Pf means nothing but your coupling factor. So I can replace, or I can write this as coupling factor. And similarly 10 log Pf by Pb. 10 log Pf by Pb means what? This is nothing but your directivity. So this will be your directivity. That means we can write isolation is equal to summation of coupling factor plus directivity. That is I is equal to C plus D. This is one of the important relationship between isolation, coupling and directivity. So in the previous discussion, so we have seen the normal values of coupling factor as 20 dB and directivity as 60 dB. So by using these two known numbers and this from this relation, so we can find what is the normal value of this isolation. That is I is equal to C plus D. C is equal to 20, D is equal to 60. So we are going to get I is equal to 80 dB. 80 dB is the normal value of isolation. So I is equal to 80 dB means what? That means this I is equal to 80 dB. So I is equal to 80 dB means this 10 will be here. So it will be 8 and this will be 10 power 8. So we will be getting PB is equal to Pi by 10 to the power 8. That means very small. Pi is our input power. That means 1 by 10 to the power 8 of the input power only you are going to get as a back power. Very negligible power. That's why ideally we used to take PB is equal to 0. But in practical we are going to get very small number like 1 by 10 to the power 8 of the input power. So here the important note is the coupling factor is a measure of how much of the incident power is being sampled. Basically sampling means we are taking from port number 3 in this particular, port number 4 in this example. So this is our input port, this is our coupling power. So how much power is being taken as a sample? For that this coupling factor will be useful. Similarly, while directivity is a measure of how well a directional coupler distinguishes between the forward and reverse traveling power. That means basically directivity is D is equal to ratio of Pf by Pb. Pf is your forward power, Pb is your backward power. So in this particular figure, So this directivity is going to tell you how much is moving towards port number 4, that is forward power, coupling power, and how much is moving towards port number 3, that is called as backward power. So this backward power should be ideally 0, but in normal cases we used to get some amount of power, very little amount of power across port number 3. So this relation we can get it from the directivity parameter. So then we will discuss about what is the S matrix of a directional coupler. So as we have seen earlier, directional coupler is a 4-port device, microwave device. So the matrix size will be 4 by 4. This S11, S12, S13, so on. And all 4 ports are perfectly matched. We have seen in the previous classes, perfectly matched means that particular port will have 0 reflected power towards the same port. So S11, S22, S33, S44 is equal to 0. And also while discussing this particular example, so we have identified that if input is given at port 1, there is no output at port 3. If input is given at port 3, there won't be any output across port 1 in ideal cases. That means port 1 and 3 are isolated ports. Similarly, port 2 and 4. That's why we are writing as S13 is equal to S24 is equal to 0. So S13 means what? Output at 1. 1 is our output, 3 is your input. So if you give input at 3, at 1 you are going to get the output. So S13 and S24 is equal to 0. And from the property of the symmetry, that is Sij is equal to Sji. So we can write S21 is equal to S12, S23 is equal to S32, S24 is equal to S42, S31 is equal to S13, S34 is equal to S43, S41 is equal to S14. So by putting all the values, we are going to have an S matrix. This S matrix, so we need to find out what is the value of these unknown values. S12, what is the value of S14, what is the value of S23, and what is the value of S34. So in order to find the values of these particular unknown parameters in a S matrix, so we will go applying properties of S matrix, mainly the property of unity and the property of 0. So as we know, the unity property means S matrix multiplied with its conjugate is equal to unity matrix. So since we are dealing with a 4 by 4 matrix, so S matrix 4 by 4, its complex conjugate 4 by 4 is equal to 4 by 4 unity. Diagonally all ones, 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. So here we can write R1 C1, first row, first column. First row, first column means 0 into 0, S12 into S12 star, S12 into S12 star means mod S12 square. Okay. Next 0 into 0 is 0, S14 into S14 star, that is S14 into S14 star is nothing but mod S14 square is equal to 1. Likewise, we can write R2 C2, R3 C3, R4 C4. Then we are going to get 4 equations, 1, 2, 3, 4. So here, and if you apply first row with the column 3, that is R1 C3, what we are going to get? We are going to get S12 into S23 star, S12 into S23 star, then plus S14 into S34 star. That we are writing as equation number 5. Basically, why we are writing all these equations, why we are applying unity property and zeroth property, the reason is in the previous matrix, in the previous step, we are having many unknowns. We need to find out what is the value of those unknown parameters in the S matrix. So for that, always we used to apply the properties of main properties of S matrix, and we are going to simplify the equations. So if you look at these 1, 2, 3, 4, 5 equations from 1 and 2, from 1 and 2, if you equate this S12 and this S12 will cancel, then you are going to get S14 mod whole square is equal to S23 mod whole square, that is S14 is equal to S23. Similarly, from 3 and 4, S34 will cancel, then you are going to get S14 is equal to S23. That means same thing you are going to get. From 1 and 2 and from 3 and 4, we are going to get S14 is equal to S23. Similarly, from 2 and 3, this S23 and this S23 will cancel. Then we are going to get S12 is equal to S34. S12 is equal to S34. So let's assume, suppose S12 is a real number. So real number we are taking as a P. Okay. Then S12 is equal to S34. Then it is equal to P. Then what is its complex conjugate of a real number? Complex conjugate of a real number is again a real number. So S34 star is equal to also P. So if you put the assumptions in equation number 5, what we are going to get? Equation number 5 means S12. S12 is what? S12 is P. So P here. S23 star as it is. S14. What is S14? Basically S14 is S23. Right? So we have written as S23. And S34 star. S34 star is P. Is equal to 0. So we can take P common. Then we are going to get S23 star plus S23 is equal to 0. Then we can write S23 is equal to minus S23 star. So this is possible only if S23 is a JQ. If S23 is equal to JQ, then only you are going to have S23 is equal to minus S23 its complex conjugate. So right now, so we know S14 is equal to S23, S12 is equal to S34, and we have taken S12 is equal to S34 is equal to P, and we have got S23 is equal to JQ. So we are going to summarize all the steps. That is, first step we have got is based on perfectly matched ports, that is S11, S22, S33, S44, that is equal to 0. Based on the isolated ports, S14 is equal to S23 is equal to 0. And this S14 and S23, S14 and S23, S12 and S34, we have got it from the property of unity and property of 0. If you put all the values, then we are going to get the final S matrix. 0, P, 0, JQ, P, 0, JQ, 0, 0, JQ, 0, P, JQ, 0, P, 0. This is the final S matrix for a directional coupler. So please note that the value of PB in ideal case is equal to 0, and also P square plus Q square should be equal to 1 in this particular matrix. So this is all about directional coupler and its applications, the geometry of a directional coupler, operation of directional coupler, and the derivation of the scattering matrix of the directional coupler. Thank you. Have a nice day.